Hello, my name is Mr. McLean. I'm the Director of Maths at Heathcote School. I'm going to speak to you briefly about our A-levels in mathematics and also in further mathematics. I'm going to speak about the breakdown of the modules for the course and the teachers that teach it in terms of how we break it down percentage-wise for the teaching allocation. So the first thing I'm going to speak to you about is the A-level, which we break up into 3 exams, which are 2 parts. Now we can see we've got pure mathematics for papers 1 and paper 2, and that covers the traditional maths that you would have done in lower school, some of your algebra, things like sequences, logarithms, which will be new to you, differentiation, integration, forming part of our calculus there. But moreover, this is the math that you build on a base in terms of what you've done before. And we also cover applied mathematics. Now, applied mathematics is statistics and mechanics. A lot of statistics you would have covered, but mechanics would definitely be new to you. Now, this is taken up 33% of the course. And if I go back, these 2 first exams make up 66% of the course. So it's a pure mathematic heavy course. Further mathematics is similar. We do papers in core mathematics, which again is very similar to that algebra heavy content that is the pure mathematics for the A-level course. Further mathematics, it goes beyond the realms of the things you'll be learning in mathematics. It's a very challenging course, but for those who achieve very highly for GCSE. When we come to further mathematics and continuing with the other exams that we do, paper 3 gives you an option of 4, of which you pick 1. This will be taught by your teachers in the year. And you've got paper 4, which again, you take 1 paper. The entry requirement for both courses is a grade 7. So you have to work incredibly hard at GCSE to access the maths course. And there's good reason for this. A-level maths is a very rewarding A-level. I really enjoy doing it as a student, as a pupil. But also it's really important that you have the skills before you start so that you can build from a good base. If you've any questions at all about the courses, please do not hesitate to either contact myself or Mrs. Nawaz Khan, who is our Key Stage 5 coordinator in mathematics. Thanks ever so much.
Hello, today we're going to be looking at how to find the gradient of a function or of a graph. If you remember from year 11, we know how to find the gradient of a linear graph, a straight line, and we've also seen how to estimate the gradient of more complex functions like quadratics and graphs that have a curve in it. And so what we're going to do today is try and find a way that we can always find the exact gradient at any point on any function. So we're going to try and use our year 11 knowledge to do this. So in front of us, we've got the graph of y equals x squared. And so hopefully we remember this from GCSE. And we're going to try and find the gradient of this function. Now, hopefully from year 11 or last year, you will remember that we can estimate the gradient of this function by finding a tangent. So a tangent is just a line that just touches the curve once and is kind of what is happening or what's going on at that point. So here I've taken 2, 4 as my example point, and I'm going to try and find what the gradient is at 2, 4. And so we started this process by looking at this tangent. Now, the only way I could find the gradient of this line is if we remember how we find the gradient of linear functions or straight lines. And so actually, let's take another example and just make sure we remember how to find the gradient of a linear function. So here I've got a second line. To find the gradient of a line, we need 2 points. So actually we would need 2 points on the graph. And so here now I've got 10 and minus 2 on the graph and also 15 and 8. So we need to actually find the gradient between these 2 points, and that will be true for the whole line. So how do we find gradient? Well, gradient is just the change in y over the change in x. So all we need to do is try and work out what the difference between our y coordinates are and what the difference between our x coordinates are. And so if we look at those distances, so here I've got a distance of 10 between 8 and minus 2. And I've got a distance of 5 between 10 and 15. So now that I know these distances, I know my change in y and I know my change in x. And so what I can then do, actually work that out 10 divided by 5, which is 2. So this graph, this line has a gradient of 2. So now let's go back to this example. So the problem with the tangent is I don't have a second point on this line. And you'll remember that when you're in year 11, and the reason it was an estimate is that we estimated what a second point on this line would be and then tried to use that. But this time, I'm not going to do that. I'm actually going to only use points on y equals x squared. So I need to, because I don't know any other lines, points on this line, I need to find a way of estimating this. So if I can only get another point on y equals x squared, I'm just going to randomly choose another point, and that's going to be this point here, 525. So I've chosen a second point on the curve. I could choose any point on the curve, up or down. And I can find the gradient of this line now because I've got 2 coordinates, and I want it to be as close to this tangent gradient as possible because I want the gradient here, but I'm using these 2 points to kind of estimate it. So if we did that while it's here, 525, they're not the same line, they're not quite right, but if we did try and find the gradient, we've got a distance of 21 for the y's, a distance of 3 for the x's, and so 21 divided by 3 equals 7. So we now have a gradient for this green line segment. However, I want the gradient of this line. Now, to improve my estimate, what I can do is actually move this point towards the other point, because as you see, this green line is getting closer and closer to the black line. The direction it's going in is getting closer and closer and closer until it's almost the same line. And the smaller I go, the better I go. And as you can see, the gradient is changing the whole time. So as I've gone down, the gradient's getting smaller and smaller and smaller. It's getting smaller and smaller and smaller until we get to this point really close to the line now, where it's just above 4. And it's going, it's going, it's going, it's going, and then it all goes wrong. Once I actually hit this, you can't divide by 0, so I've gone a bit too far, and so I can't quite see what it is. But if I go just a little bit more, I've got a gradient 4.05. And I think if we're thinking, if that one's going to be really close to the true gradient of this line, I would hope it makes you think that, well, 4.05 is really close to 4. And so it feels like 4 must be the answer to the gradient of this line. And we're actually going to try and prove that. We're going to try and find a way of proving that 4 is indeed the gradient of this line. So I'm going to go back a bit. Not as good there. Again, much better, although you can't really see it there. And we're getting closer and closer to 4, so we think 4 is our estimate. Okay, fair enough. Well, let's take a different point on the line, a general point, and see what we can do with a general point. And then we'll come back to the example of 2, 4 again. So a general point would be just any value of x and any value of y. But you'll notice I haven't written y, I've actually written x squared because we know that y equals x squared. So this point is an x value and an x squared value, but that could be anywhere on this curve, that x and that x squared. Now we know to be able to find the gradient, I need a second point on my curve. Otherwise, I haven't got anything to go with. So I've chosen a second point here. And this point is just a bit further in the x direction. And so I'm calling this x plus some extra number. So I've gone a little bit further in the x direction. And as a result, now what's being squared is the x plus h. So again, the y, which is whatever's going in squared, is now just x plus h. So we've got a second point that is x plus a bit more, and that is going to become x plus h squared. And again, that could be anywhere here. But we know that the closer it is, the better the estimate for the graph is. And you can see the line here is almost exactly the same as the line of the curve, whereas up here, you can see a difference between the black line and the purple line. So can we then use this to try and find the gradient? Well, we know how to find gradient. That's going to be the change in the y with the change in the x. So here, our change in the y, well, our y is x plus h squared. And this coordinate here is the y, x squared. So we've got to do x plus h squared minus x squared to get the length of this line. And here we've got x plus h, take away x. And so that's going to give us our x difference. So when we're finding the gradient, we now have the change in y over the change in x. Once we've done this, we need to actually try and simplify this algebra or work out the algebra, make it as simple as possible. The only thing we really can do at this point is actually do x plus h squared and expand these brackets. Now, if we're expanding these brackets, it's really important that we remember everything inside these brackets is getting squared. That doesn't mean that we're doing x squared plus h squared. That means x needs to get multiplied by an h, x needs to get multiplied by an x, and then again. So really this is x plus h times x plus h. And so that is a kind of a quadratic expansion. And if we do that, we're going to get x times x is x squared, h times x, another h times x, and then h times h is h squared, and then we've still got my minus x squared, and then x minus x is nothing, leaving us just with this h. So if we now simplify that, we can actually put some of this together. Well, x squared minus x squared is going to cancel out. Hx plus hx is going to be 2hx. So now we've got this, but what we notice is we've got h's everywhere, so I can divide everything by h. And so now I have an answer of 2x plus h. And we're really close now. So we've done the algebra, and so it's suggesting the gradient is 2 times whatever our x value is, plus this extra little bit. But what we've said is that this extra little bit is how far this point has moved on. And our estimation is going to be better the smaller that extra bit is. So the closer we get to our x, the better our estimation is going to be. In fact, it will become perfect if we manage to make that distance nothing. And so this is a skill in mathematics, and it's called limiting values. So what we do is we look to see what happens as h gets closer and closer to 0 until eventually we make it 0. And so basically, once h has become 0, I'm just left with 2 times x. And so the gradient anywhere on y equals x squared is just going to be 2 lots of the x value. And so if we go back to our tangent example here, where it was 2, 4, the x value is 2. And if you remember, our estimate was 4. 2 times 2 makes 4. So this one is in fact 4. Now, if we took another point, let's say if we took the point 3, or an x value of 3, then the gradient would be 6, because we've got 2 lots of 3 is 6. So what we could do is always consider the general point and this idea of using our linear way of finding gradient and then trying to apply a limit as h goes towards 0. And we can do this with any function. Obviously, as functions get more complex, the algebra here becomes a lot more complex. And so we'll go through those in other lessons, but we have successfully managed to do it for x squared. Now I would like you guys to have a go at seeing if you can apply a very similar method, but this time to the graph y equals x cubed. See what you can find.